Welcome. In this lecture, we are going to discuss the experimental case study with and without load current feed forward. And in the previous lecture, we have seen some analytical aspect of output impedance with and without load current feed forward. So, first we will talk about load current feed forward in mixed signal current mode control, some implementation aspect, then experimental load transient performance and comparative study with and without load feed forward. So, if we talk about this mixed signal current mode control, this we have discussed multiple times, and from this part to, if you consider this part, so this whole part will be, we have to synthesize inside the FPGA. So, this is a FPGA platform. So, this can be CLAVE or any other platform, but we are going to do, these are the digital control. The other part are analog. So, here we are using this estimated load current. Now, the question is, since this part in digital, that means we are talking about this part, so this part in digital. Now, we can actually, that means we have to synthesize this block, and this is your mixed signal block, where the data out to the ADC we have discussed, it is the ADC data, and we can use a different color actually, we can use different color. So, this data going out is the ADC data, then the DAC data is nothing but which is here coming out, then naturally the comparator output will be from here, like that. We know all this aspect. Okay, so we can now, since this whole thing in digital, so this is in digital, we can use FPGA, we can use digital IC, whatever, it depends on implementation platform, but this thing in digital. So, inside digital, if we communicate with the processor, that means I will say here we are talking about digital communication. So, if your power management unit, the controller can communicate with the processor, then the processor know what task is going to come, and that gives you an estimate of the load current, and that is why we are using this load estimation inside the digital platform, and we will be considering if the load step size is perfectly known or there is some variation, then how the output voltage is going to get affected, and if we do not consider load feed forward and if we consider load feed forward, what is the response in the output voltage. So, here the implementation aspect we have discussed, that this is where the ADC data is going and this is where our DAC data is going out. Then again we have to discuss, and this block is nothing but your this, and as if we have included the processor is part of information is available. So, it is a part of digital communication. So, this is also a part of digital. So, these are all digital. So, this is the estimate of the load current. Now, we are going to consider experimental case study. First, we already have discussed multiple time about the power stage. So, what was the inductor? 1.8 microhenry, capacitor is 200 microfarad, and we are changing the load resistance from 13.5 to 0.33, and we have considered the simulation, whatever we made simulation. This is our Kp, all discrete time, this is our Kid, that is discrete time integral gain, and we are considering 1 volt. Now, we are making a load step. So, this is a load step transient which is designed, that means our crossover frequency is designed by considering switching frequency by 8, and since it is current mode control, so it is a sluggish response. You can say the response is sluggish, I can say the slower response. I can say it is a slower transient response. but it is a well dam. Okay, slower transient response, because what is the undershoot? Undershoot is coming to be, this undershoot is coming around 100 millivolt, but this is coming to be around 80 microsecond, which is pretty large, and that is the problem. In fact, in voltage mode control we got around 30 microsecond, because if we use the alternative design approach we can get an indirect load feed forward action. So, that is why it was coming to be much smaller, but here it is large. And if you see the step here also, it is like 100 microseconds, something like that, nearly 100 microseconds, and the overshoot is also roughly around 100 millivolt overshoot. And this is a typical current mode control slower response, looks like something similar to a first order system. Now, we are considering load step feed forward, where assuming the load step, because we are making one load current to the other load current. So, here it was 70 milliampere and it is going to like a 3 ampere. So, this load step size, I would say, if this is perfectly known, and we are calling this as a I0 estimate, as if it is a digital value that we are giving inside the digital controller platform. You can see overshoot is totally cut down, there is no overshoot, and insignificant undershoot. That means what we learned, that closed loop output impedance with load feed forward was approximately 0. If it is 0 perfectly, then it should not have any overshoot undershoot effect. Overshoot is almost like a vanished, undershoot should also be vanished if it is exactly. But because of the practical limit, because inductor current, if you consider this, so there is a slew up process, right. So, that means inductor current was like this, now it is slewing up, right, sorry. So, inductor current, it has to slew up, right. So, this slew up depends on the slope m1, and what is this? It is V in minus V0 by L. Since it cannot reach immediately, if it could have reached like this, then there should not have been any undershoot. But since it cannot go, this is a physical limit comes from the slew rate limit, and that is why slight undershoot will be there, bound to be there. So, that means practically it will not be exactly 0, but it is nearly 0, that means effect can be negligible. This is the case where the load current is perfectly known, that means we know the I0 estimate almost accurate, it is like accurate. But what happened the second case, if the same condition, if I0 estimate is about 0.9 time your actual load step size, it is a digital number, then what will happen? Again, overshoot is also negligible, almost no overshoot. Again, kind of small transient effect, I will say negligible transient effect. Transient effect, but this is much superior than without load feed forward. That means, even if you get some partial information of the load current, say you can further reduce, maybe this will get a little bit more deteriorated, but it will be far better than without load feed forward. So, in bottom line, if we incorporate this information, you will get, and if you compare this, that means this is without load feed forward, this is 90% accurate load feed forward, and this is like a 100% accurate load feed forward. So, these two are more or less identical transient performance. You can see they are closely transient identical performance. So, it is because 90% 100% are almost close. Okay. So, you will get the transient performance almost identical. So, this is much superior than without load feed forward. Now, we want to show the same thing if we have increased the load step size. What was the load step size here? our load step size here was nearly 3 ampere and it was at 1 volt output. Now, we want to change the load step size is nearly 5 ampere at 5 volt, sorry, at 1.8 volt output. Another thing, this was an input was 3.3 volt input and here input is 5 volt input. Okay. So, this is here 5 volt input, 1.8 volt output. Now, the first thing again the load transient performance. Here you can see it is in the 5.5. So, this division is 0.5 volt. So, you can see undershoot it is 1.8, around 300 millivolt undershoot and overshoot is around 250 millivolt overshoot, and the settling time is coming to be it is in the 40 microseconds. So, it is roughly around I will say 35 microsecond and here it is like around I would say 40 microsecond. Now, if we add the load feed forward, you can see almost negligible effect. Here also very smaller undershoot. That means, even for a such load transient, the effect is almost, there is almost insignificant effect in the output voltage. So, as a result you can make fast transient performance. Okay. So, that means what we saw in summary, load current feed forward in mixed signal current mode control we have discussed, and we have shown experimental transient performance with and without load current, and we have made comparative study with and without load feed forward, and we saw that load current feed forward can significantly cut down the undershoot and overshoot. As a result, we can reduce the output capacitor size, because if you go back to the result, if the undershoot and overshoot of the output voltage can be reduced, so you can actually decrease the output capacitor size. As a result, your power supply size will come down, because the capacitor in the output takes a significant, occupy a significant space, and you can reduce that, you can reduce the bill of material, and this will also help in the reference transient performance, because if you use a smaller capacitor in the output, you can change very fast output voltage from like a DVS. It will allow fast DVS slew rate with reduced current undershoot. So, that means this feed forward action in digitally, if you can estimate and if you can communicate with processor, you can make the power supply much faster and superior. So, in summary, all these points we have discussed, and comparative study shows that this effect can be explored in digital control, and this is how the digital control can make much faster response compared to analog control counterpart. That is it for today. Thank you very much.